So let's try out this example. We've got a function f of x equals 2x cubed plus 3x squared plus 1. And we want to find the intervals where this is increasing and where it's decreasing. So in other words, we're going to figure out where it's increasing. We want to solve when f prime of x is positive. And where is it decreasing, we're going to solve when f prime of x is negative. So what we'll start with is we'll just take f prime. We've got 2x cubed plus 3x squared plus 1. So 6x squared plus 6x. 1 is a constant. So our derivative will just be that. And then set this equal to 0. If you want, we could find the critical values. So factoring out the 6x, we get 6x, x plus 1. So our critical values will be at x equals 0 and x equals -1. Okay, now this is why I want to pick these values to start with, is because now this kind of gives me some good information. These are the points where we know our function, our derivative could change from positive to negative or vice versa. So the critical points are going to be essential for solving these inequalities that we have up here. So that's always how I'm going to start this out. I find my critical points, whatever they are, and then I create a number line, or what we're going to call a sign chart, which is a number line. So this is what I'll call this, a sign chart, which is just a number line that has the critical points on it. So basically any points where you get 0 in the numerator or denominator of my f prime. So in this case, -1 and 0. And then we test on this number line, when is f prime positive and when is f prime negative. Okay. So the idea here is we test where f prime is positive and where f prime is negative. So we kind of have these boundaries where f prime is equal to 0 at -1 and 0. So those create sort of the points where it could potentially change sign. So one way I could approach this is I could just look at these two factors in our f prime. So we've got 6x and I've got x plus 1. So you can look at these two factors, like 6x we know will be positive when x is greater than 0. So it'll be positive on this side over here. So any value of x that I put in that's positive will give me 6x is positive. And on the other hand, it'll be negative when x is less than 0. So it'll be negative on all these regions here. And then the x plus 1 factor, well, that'll be positive when x is greater than -1. So it'll be positive on this side of -1. But it'll be negative when x is less than -1. So on this side here. Okay. And so putting these two pieces together, let's now remember that f prime is just made up of the product of 6x and x plus 1. So if I do a negative number times a negative number, we're going to get a positive value here. if I do a negative times a positive, we're going to get a negative number here. And if I do a positive times a positive, then we're going to get a positive number here. Okay. So this tells us exactly all the information that we need to know, right? That here f prime will be positive on the intervals here from -infinity to -1. And it'll also be positive over here on the interval from 0 to infinity. Whereas here in the interval from -1 to 0, it's negative. Okay, so you can visualize here that our function is increasing over here, decreasing here, and then it's increasing here. Right? So to kind of answer the question now, what are the intervals where it's increasing? Well, we showed here that it was the derivative was positive on the interval from -infinity to -1, and then on the interval from 0 to infinity. And where was it decreasing? Okay, and over here we showed that the derivative is negative on the interval from -1 to 0. Okay, so this is kind of something we're going to do a lot in this section. This sign chart that I'm making here, because it helps me analyze where the function is positive and where the function is negative. Okay, do you guys have any questions about that sign chart right now? We'll see it a little bit more in some future examples, but do you guys kind of understand how I pieced it together at least a little bit?
For the top part where you drew the positive and negative sides, like where it has the arrow going up or down, how did you decide that again? Is that because two negatives makes a positive? And
Yeah.
oh, okay.
Yeah,
Okay.
exactly. Because we see that 6x times x plus 1, we're multiplying those two factors together.
Yeah.
So it's like when I multiply 6x times x plus 1 on this
Yeah.
interval, you're going to
Oh,
have a
okay.
negative times a negative,
Yeah.
which makes it a
Okay.
positive, right? Yeah.
Okay.
And then
Thank
here,
you.
a negative times a positive makes it a negative. And here, a positive times a positive makes it a positive. So it just kind of gives me a rapid way of doing it. Sometimes what people like to do is if they have a hard time thinking about this kind of thing, like what I'm doing here. Sometimes you know, I might do it this way, where instead of just analyzing the individual factors, I could say, well, let's just pick a test value somewhere on this interval. Like I can test out you know, x equals -2, because that's sort of like a representative from this interval. And I can just check, what do I get when I do f prime of -2? And you could just plug it in here, and you'd probably you know, have to work out some basic arithmetic there, but you get in this case you get -12 times -1, so you get a positive 12. You get a positive value, right? So that's another way you could do it, is you could kind of pick test values to help you analyze it. And that way that kind of shows you that, okay, with this one test point that I tried, well, that kind of represents any value of x on this interval. So any other value of x that I choose on that interval, I know would have to have the same sign. So if I choose a different value of x, then I can assume that f prime would have the same sign for any other value of x on that interval. So it's kind of like picking a representative, or here I would choose, maybe this one's maybe a little bit trickier, but I could choose like f prime of -1/2, for instance. you'd see you get a negative value. Or here f prime of, say, +1, and you'd see that you get a positive value. So this is just kind of picking a test value. So this is like a x equals -1/2 is a test point. So I might do it this way sometimes, but at first it kind of helps me to just think of it more like this, where I'm looking at each of those individual factors that make up the derivative and thinking about how the sign of each of those factors changes as x changes. Sometimes it's simple enough to do it that way. So let's see. Here's just a picture of the graph that we can kind of see matches what we just showed. Actually, there's two pictures here. One is the original f, which is the black curve, and then the derivative curve, which we kind of analyzed on the number line, right? So when we analyzed the f prime, we showed that f prime was positive when x is on the interval from -1 or from -infinity to -1. F prime is negative between -1 and 0, so it goes below the x-axis there. And then f prime is positive when x is greater than 0. Right, so you see the sign of f prime goes from positive here, negative here, and then positive here, sort of like what we observed. And we see that kind of also correlates with what we said about the original f. The original f is increasing from -infinity to -1, and then when it gets to -1, then it changes to a decreasing function, and then it decreases until it gets to 0, and then it starts increasing again. So, oh, yeah, and by the way, before I look at the next picture, let's think about those critical points that we found were points where it changes from increasing to decreasing. Like at this critical point here, notice that it was increasing before it got to that critical point, and then it's decreasing after it. So that would mean that this is a local max here. And this one's the other way around. This one is decreasing before it gets to that point and then starts to increase afterwards. So that one's going to be a local min. So that's what we'll notice here is when we have the sign of f prime changes from negative to positive, that means we have a local minimum value at that critical point. Versus if our f prime changes from positive to negative, then we have a local maximum at that critical point. So that's going to be helpful for us when we want to identify the points where we have a local maximum or local minimum. So okay, looking at this kind of a little bit more complicated looking picture, the idea is we can notice what happens at each of these critical values to help us figure out what makes it a local max or local min, or maybe it's neither. So like we know that we could have an absolute min that occurs at one of the endpoints, like over here, this is an absolute min because that's the smallest value overall. Here at this first critical point here, we notice that it's not a local max and it's not a local minimum. And the reason is because even though it has a horizontal tangent, the derivative stays positive on either side, right? So f prime of x is negative or is positive on the left side of that first critical point, but it stays positive here on the right side. So it continues to increase. So it's increasing before, but it continues to increase after. So this is neither a local max nor a local min. Then we get to this critical point here, where we see it's increasing before it gets to that point, and then is decreasing after it. So at that point, we have a local max. So it's a critical point because it's got a horizontal tangent. It's increasing before, decreasing after, so we know that makes it a local max. If we look at the next critical point, again, here it's a critical point where we have a horizontal tangent, where it's decreasing before it gets to that point and then increasing afterwards. So we see that one is a local min. So it's decreasing before, increasing after. And we notice also the derivative is changing from negative on the left side to positive on the right side. Okay, so f prime changes from negative to positive means it's a local min. And then looking at the next critical point up here, notice that this one is a local max. And we can again identify the same property here, that it's a critical point because it's a point where the derivative is undefined. Notice it's got a hard corner in the graph there. It's got a sharp corner. So it's changing from a positive derivative on the left side, it's increasing, and then a negative derivative on the right side, so it's decreasing. So it's changing again from increasing to decreasing. So from left to right, it goes from a positive slope to a negative slope. So we see that that would be another point where we have a local maximum. And again, it's also an absolute max because it's the highest point overall. And then looking at this one, again, here we have a critical point because it's got a horizontal tangent, but because it doesn't change from increasing to decreasing, it just continues to decrease on either side. This one would be neither a local max nor a local min, so no extreme value there. So in this picture, yeah, this is what we should look out for, right? Is all the different ways that you can think about it. But the key thing is that a local maximum occurs when it changes from a positive derivative to a negative derivative. And a local minimum occurs when it changes from a negative derivative to a positive derivative. So that's what we're going to actually call our first derivative test. So assume f is continuous on an interval that contains a critical point c. And assume f is differentiable on an interval containing c, except perhaps at c itself. If f prime changes sign from positive to negative as x increases through c, then f has a local maximum at c. If f prime changes sign from negative to positive as x increases through c, then f has a local minimum at c. And if f prime is positive on both sides near c, or negative on both sides near c, in other words, if the sign does not change, if it doesn't change from positive to negative or from negative to positive, it stays the same sign, then f does not have a local extreme value. Okay, so that's kind of just formalizing what we observed in the graph, but this is what we're going to call the first derivative test. Okay, so in fact, what you can use the information that we gathered in that sign chart. So like if I go back to that example we did a moment ago here where we made the sign chart, notice that the sign chart actually gives you all the information that you need to know to use the first derivative test. Because we can see at -1, for instance, it changes from positive to negative. So we know we have to have a local maximum there at 1, or at -1, excuse me. And then at 0, it changes from negative to positive. So we know we have to have a local minimum there at 0. Okay, so that's how the first derivative test is going to work. It just helps us just determine where the local maximum or local minimum values occur. So let's try here with another example. So we're basically going to just go through the same process again, where we find f prime, and then we analyze the derivative of f prime on an, we analyze the derivative f of f prime. We analyze f prime on a number line so that we can figure out where it's positive and where it's negative. And that tells us a bunch of information. It tells us where f is increasing, where it's decreasing. And it also tells us where we would have any local extreme values, any local maximum or local minimum values. So it kind of gives us a whole bunch of information that we can then use to, for instance, piece together a very informative graph about this of this function. So let's do that. Let's go through and we'll start by finding f prime. And let's see, so here we'll have 12x cubed minus 12x squared minus 12x plus 12. Okay, so a bunch of 12s. And like usual, we should start by trying to figure out what the critical points are, because that'll help us split up our number line when we're making the sign chart. Let's factor out a 12 here, I think would be an easy way to start. Okay, so I got x cubed minus x squared minus x plus 1. If I want to factor this, what can I do? Do you guys know any good tricks for factoring something like this?
Is it the one where you have to do like x minus 1 times x to the power of n minus 1 or something like that?
Not quite. Grouping, right? Yeah, so somebody mentioned grouping. Yeah, that's what I'll do, right? So remember, you can try grouping the terms like this, right? So if I take out the common factor between x cubed and x squared, which should, I guess, just be x squared, right? So that leaves me with an x minus 1. And then same here, I can take out a negative 1 between these two terms. And that leaves me with the same thing, x minus 1. And then I can factor out the x minus 1 between those two terms. That leaves me with x squared minus 1. X squared minus 1, I can go a little bit further with that, right? That's x minus 1, x plus 1. Okay. So here with that, we can see our critical point. Well, actually, there's two critical points because we got x minus 1 squared here, and then x plus 1. Yeah, I can also bring down the 12 here. Notice the 12 won't really make a difference because that's not going to change the critical point, but it will make a difference sometimes if I have a negative constant in front. It will make a difference when I make the sign chart. So I'm going to bring down that constant with me here. So here's just our factored form of f prime. So then we set that equal to 0. And I get my critical points here. So x equals 1 or x equals -1. So remember, those are the points now I'm going to put on my number line. So let's create the sign chart. I'll write it over here. Okay, we had the critical points at -1 and +1. Let's see, so we've got, yeah, these, actually there's these three factors we've got. So we'll kind of I'll do it the way I did it a moment ago. In the previous example, we got 12, x minus 1 squared, and x plus 1. So actually notice that 12 is always positive, so we can kind of just go through and put positive everywhere. X minus 1 squared, because it's squared here, notice that this one is also always positive. Anything that's squared is always going to be positive. So the only one that changes sign is x plus 1, which will be negative when x is less than -1. So it'll be only negative here, and then positive on the other two intervals. So piecing it together here for f prime, we see it'll be positive on this interval because you got two positives, or I'm sorry, it'll be negative because you got two positives and one negative. Negative there. It will be positive on the other two intervals because those are all positive factors there. Okay, so we've kind of pretty much figured out everything we need to know, but let's put the pieces together now. So remember, when f prime is negative, then that means that it's decreasing here. And then it'll be increasing when f prime is positive, so it'll be increasing on those 2 points, or on those two intervals. So we've got the interval here from -∞ to -1, where it's decreasing. We've got the other two intervals over here from -1 to 1, and then from 1 to infinity, where it's increasing. So to answer part A here, I'll just put it up here. So it's increasing on the intervals from -1 to 1, and then also from 1 to infinity. And it's decreasing on the interval from -∞ to -1. So what about the second question? So identify the local extrema. So what would you guys say there?
-1 would be a local minimum.
Very good. Because we noticed there it changes from decreasing to increasing. So the point there where it changes will be our local minimum. Good, so we have a local minimum. At x equals -1. Good, and what about our local maximum? Do we have a local maximum?
No,
No,
because
why not?
like the 1 is just like a flat line where it just stays positive on both ends.
Yeah, good. So it doesn't change from positive to negative. It just keeps going up, right? So it kind of levels out for a moment, but then it keeps increasing. So we actually have no local maximum. So you see actually a lot of information that we can extract from this first derivative test. Okay, and here let's, I think I have a picture of the graph here somewhere. So that's just our sign chart. That's the same sign chart that we made, right? And here's the picture of the original f there is in the black, right? Got the original f, and then f prime is the one in the red. So we can see that, yeah, when f prime changes from negative to positive, that's where we had that local minimum value. And at this point, f prime doesn't change from positive to negative, so stays positive on either side. So that's not going to be a local max nor a local min. So it kind of levels out for a moment, but then it continues to increase. Okay. So let's try another example. I think we did something similar to this in a previous section. So find the local extrema of g of x equals x to the 2/3 times 2 minus x. So here I want you guys to try it out here. So if I distribute the x to the 2/3, then you get 2x to the 2/3 minus x to the 5/3. Remember, that makes it a little bit easier to take the derivative. So here, I want you guys to try this out. So start by finding g prime for me. I'll give you guys a second. I'll be right back. already. So using this form of it that we wrote here to take the derivative. So we should get here 2 over 3 times 2 is 4 over 3. X to the, let's see, 2 over 3 minus 1 will be negative 1 over 3. And then for the next term, we'll have 5 over 3. X to the 5 over 3 minus 1 will be 2 over 3. One thing that I can do here, this will actually help me analyze the derivative a little bit more easily, is try and combine these terms together. So I can write this as 4 over 3x to the 1/3 power. So to get a common denominator here, I'll multiply x to the 1/3 over x to the 1/3. So that'll give me x to the 2/3 times x to the 1/3 is just x. So I have 4 minus 5x over 3x to the 1/3. Okay, now remember here that the critical values are going to be from the numerator and from the denominator. In other words, when it's equal to 0 in the denominator, we know that's going to be a point where the derivative is undefined, so that could be a critical point. So we'll use the zeros from the numerator and denominator to give us the critical points. So remember here, we'll have 4 minus 5x equals 0. Gives us x equals 4 over 5. And then 3x to the 1 over 3 equals 0. That gives me x equals 0. So those are my critical points. So let's use those to make our sign chart. So we've got, let's see, so our actually call it G prime instead of F prime. So our G is 4 minus 5x over 3x to the 1/3. So what I can do is just look at those two factors separately, 4 minus 5x and 3x to the 1 over 3. So let me think about 4 minus 5x for a moment. Notice that this one's going to be positive when x is less than 4 over 5. So it'll be positive for all the values of x over here. But when x is greater than 4 over 5, then you got 4 minus something that's bigger than 4. So that would be a negative value. And then looking at 3x to the 1 over 3, well, we know that one's going to be positive when x is positive. So when x is greater than 0, it'll be positive for all these values. And it'll be negative when x is on this side over here. Okay, so that means that when I divide them, we see that G prime will be negative here on this first interval. So a positive divided by a negative will be negative. Positive divided by positive will be a positive value. And then a negative divided by a positive will be a negative value. Okay, so here we see G prime is negative on this interval, so it's decreasing here. G prime is positive on this interval, so it's increasing here. And then negative on this interval, so decreasing here. And we see at these points in particular, at x equals 0, it changes from negative to positive. And then at x equals 4/5, it changes from positive to negative. So that will be where we have our local minimum value at x equals 0 and our local maximum at x equals 4/5. And by the way, if you want to get the actual value that those local max or local min, what those actual function values are, you can plug those values back into the original. And maybe here I've got a, yeah, there's the graph that we can see. And this slide is just the same thing as our sign chart that we just made. But here's the graph of the function. You see it's actually got this sharp corner at x equals 0, because that was where this derivative was undefined. So it's got a cusp there. But we see that that's a local minimum value because that's where it's changing from decreasing to increasing. So there's where our local minimum occurs. And then here was where our local maximum occurs, where it changes from increasing to decreasing. Okay. Anyways, do you guys have any questions about this example? Like, how do you guys feel about doing this part with the sign chart?
I feel pretty good so far.
It's all right. Okay. So yeah, as long as you guys are okay with making the sign chart, I think that's going to be the main tool that we're going to be using for all the tests in this section. So let's actually look at just a couple more things before we get too far down the rabbit hole. Actually, I think the other thing that we're going to look at in this section is the doing the sign chart again, but for the second derivative, and that'll tell us some other information. But let's look at what this theorem is saying. It says that if I have a function that has exactly one extreme value, then I know that must be our absolute extreme value. In other words, if I have one local maximum, then that must be our absolute maximum. You can think about maybe the graph that would go along with that. So if I only have one local max, that means that the function must be, you know, increasing before it and decreasing after it, and that's the only point where that occurs. So there's only one possible place that's a local maximum, means that that has to be our local max and our absolute max. Or similarly, if I have a function that has only one local minimum, so it's only got one point where we know it changes from a negative slope to a positive slope, then that has to also be our absolute minimum. It's a local minimum and an absolute minimum. And yeah, so here's another kind of way to look at it. So we know that if it has only one absolute minimum, or sorry, one local minimum, then there won't be any other local extreme values in the graph, because if it did, then then we know that has to be the absolute minimum, because if it wasn't, then the graph would need to turn around at some other points later on. So then you would have other points that are local extreme values. So just another way to picture it. So if I want to verify that this function here has an absolute extreme value on its domain, let's go through and we'll find the critical points and see what we can deduce from that. Okay, so again, it's more practice making the sign chart. Okay, so we've got 1/4 x to the fourth minus x to the third plus 3/2 x squared minus 9x plus 2. Okay, so let's do f prime now. And let's see, 1/4 x to the fourth will get, let's see, 1/4 times 4 is just 1 x to the third minus 3x squared. 3/2 times 2, so that'll be 3x. And then minus 9. Okay. This one kind of looks like another one that we can do grouping with, right? We can group. If I take out an x squared from those two terms there, x minus 3. If I take a 3 out from those two terms there, I get another x minus 3. So factoring this, we get x minus 3 comes out, and then x squared plus 3 is what's left over. And now looking at that, we see that the critical points, when I equal this to 0, we have just one critical point, x equals 3. Notice x squared plus 3 does not give me a critical point. So this one, when I set that one equal to 0, does not give me a solution. So no real solution. So this is our only one critical point here. And we can see that at that one critical point, if I choose a value of x that's less than 3, you know, you can even do this in your head. You put 0 or 1 or something in here. You'll get a negative value times a positive value, so it'll be negative on this side. And try something greater than 3, and you get a positive value on that side. So you see it's changing from negative to positive, so we have a local min. At x equals 3. And since we know it's the only local extreme, it's also a local, or sorry, an absolute minimum. At 3. Okay, so we can imagine that, yeah, the graph is going to reach a minimum at 3, but then it's going to kind of continue going up in either of the other directions. Okay, so anyways, here's just the graph that we can see why that's the case.